All right, let's talk about the RS Logix simulator. And what I love about the simulator is not the graphics. I realize the graphics are kind of antiquated, but the behavior of the software really mimics real-world applications very, very well. I have found little, if not any, problems with this simulator, other than some slight annoyances at the way it behaves that I wish were a little differently. But as far as the coding part, it seems to be very sound. I'm in it now, and you can see this is the landing screen, and I'm going to adjust mine where you can see more of it. This doesn't do anything, it's just a picture. But if I go under simulations, you'll see I/O simulator. And this simulates the LEDs you would see in an I/O rack in the real world, and does a pretty good job of that in and of itself. So just to give you an idea of what that might look like, I'm trying to find one here in a picture so you can sort of see it. So this one's not turned on, but I'll bring you a picture over to let you see it. And you can see there's LEDs either up top or on down the line here, probably up top on this particular one. Used to be years ago, they were just on and off LEDs that would appear here. Now they usually have the number lit up top of the bit that's on. And here's one that shows that even a little better than the first picture. This shows the inputs and output bits. I can't really tell if these are all inputs or all outputs, or a combination of both. I'm not familiar with this particular brand, but we can see 1, 2, 3. I know it's kind of blurry on your screen, but it's there, and it's just indicating that bit is receiving a signal that it's on. And you can see right here, even though I have no program written, I've got bit 0 on of this input card. Notice this is an input card, this is an output card, this is an input card, and this is an output card. Well, inputs are obviously switches and sensors, things that come on when they're pressed or something gets near it or something closes it. So we have different types of switches. Some of those are limit switches where they're physically moved by something coming in contact with it. Some of them are proximity switches where they're physically not physically moved, but if something gets nearby it, it will cut on. One example of a proximity switch is when you walk to Walmart and the door opens automatically. There's some type of proximity switch that saw you there. You didn't touch it, you didn't press a button, but the door opened. It performed an output based on an input. And that's all these PLCs are doing. The simulator, even the I/O here, and we could do a lot just with this. I'm going to show you there's some more stuff there. But you can right-click on these things and change the type of switches. So there's a switch that when I press it, when I left-click, it closes and stays closed. When I left-click again, it opens and stays open, and we can see the corresponding bit reacting to that. I can right-click on it and change it to a momentary. When I hold down the click, it's on, but when I let go, it goes off. And as we all know, there are different types of switches in this world. Your horn in your automobile is a momentary switch. You don't flip a switch and it just keeps blowing until you flip it again. You press it and your horn signals, and when you let go, it stops. But a light switch in your home or here at school is this type of switch. When I close it, the light's on. When I activate it again, the light goes off when I open it. So there are different types of switches and sensors and things, and their behavior is based on what we need to do. Now, these outputs are not going to come on until we write a program that makes them come on. And all a PLC does is it accepts inputs from switches and sensors, and it turns on outputs that go to motors and lamps and basically anything that we cut on and off, we can turn on and off. And it does that based on the programming we give it. So if there's no program, there's going to be no outputs. But however, let's just write a quick program here. And you should learn all about these commands in the book. I'm not going to spend a bunch of time going over what they are, but this is an input command. It kind of looks like the letter I split into. There's one half of the I. There's the other half of the I. So we're going to look at that switch. We're going to examine the state of that switch. And based on whether that switch is on, we're going to turn on an output. Now, I could turn on output 2, bit 0, or output 2, bit 1. Or I could turn on output 4, bit 3. It's ultimately up to me. But here's an output energize command. And if you look, it looks like the letter O has been split into 2. So let's do output 4, bit 2. Again, it could be whatever output we choose because it depends on what terminal we assign that output to, just as it depends on what terminal we assign this input to when we're wiring this up. And that's all we'd be doing, is wiring a switch to this input, wiring another switch to that input, proximity sensor here, a limit switch here, just depends on what we're doing. And then we're going to wire up motors and lamps and all kind of pumps and all kind of different things that we want to turn on and off to our output cards. So either the output 2 or output 4 is where we'd wire our output. So all I've done is written this program on the computer, and in the real world I would have to download it. And notice I'm in program mode, but I want to go to run mode. Now when I close this switch here, we should see this output come on, output 4, bit 2. So let's see if that happens, and sure enough, it does. And let's just say you wanted to play with this and you wanted that to be a green lamp. Well, you can right click on it and make it green. So there we go. When I open it, the lamp goes off. When I close it, the lamp comes on. So we just control the light with a switch. Pretty basic, pretty easy. And we can make things happen. So let's do another switch just for fun of it. So I'm going to go to program mode. Now my processor is still running. It's still doing things back here, but I'm programming, and until I download it, nothing's going to happen here. So I'm going to add another switch here, and we'll use 4-1, and I mean 1-1, excuse me, I said 4-1, and we'll turn on, let's turn on the one above it, why not? So we got to put the output instruction first. Whoops, I already had. So we'll right click on it and delete it. Where's delete? Cut. Yeah, there we go. So we'll do 4-1. And just so you understand this addressing, this is input slot 1, bit 0, 1, 2, 3, 4. Output slot 2, 0, 1, 2, 3. Input slot 3. Output slot 4. So these are just like street names. Input slot 1, bit 0, bit 1. Just like we have unique addresses on our street, we have new unique addresses in our slots here. So this would be output slot 2, so forth and so on. So all 64 of these inputs and outputs. Now how did I come up with 64? Well, there's 16 in each one because we go 0 through 15. All 64 of these addresses are unique. So I could say input 3, 12. So there's input 3, there's 12. So unique address, nothing else could be input 3, and nothing else could be 12 on input 3 without first going to input 3. So there we go. So we're going to download that, and we're going to hit run. And we're going to see that these lights will function independently of each other. And we can turn them on and off based on the state of these switches. Now, the one thing that throws people a little bit, just remember how PLC works. Hopefully you've read your book by now and you understand it. All that is happening in all PLC is a computer. The computer is looking at that switch and it's saying, okay, yep, I'm receiving a signal from that switch. So this bit's going to turn on. And when I do that, I'm going to write a 1 in the data table indicating on. Because remember, when we're talking about discrete devices, they are either on or off. So this bit is now a 1. And we can actually look at that. If we go to help, where is it? Settings, maybe? I know it's in here somewhere. I just can never remember where it is when I want to find it. somewhere is the data table. Hang on a minute, and I shall find it. It's actually hiding in plain sight. It's right here. So notice it defaults to the output table. So let's watch our output table change. Notice output 0 is nothing because we don't have a slot 0 here. Some processors, some racks do have a slot 0. We do have an output 2. We don't have an output 1 because it's actually an input card. And we have an output 4 because it's an output card. So if we scroll over and go back to run, because I'm not in run mode, we'll see bit 2 is on now, indicating that output 4, see output 4 bit 2. Watch what happens when I turn off that switch. That output goes off and goes back to a 0. We turn on this one and this one, and we'll see both of them come on. Now we can go to the input table as well, and we can see both input slot 1, bit 0 and 1 are on, and we can watch those go off when I do it. So all that's happening is this computer is receiving a signal. It's writing either 1s or 0s based on the state of these switches into the input table, and then it writes a 1 or a 0 in the output table based on the programming and what output should be on. So right now it's writing all 0s to everything because nothing's on. Let me go back to the output table. So it's down here somewhere. Oh, that's interesting. I can't see. There it is. It's hiding from me. It's up top. So there's the output table. But when I manipulate my inputs and turn my outputs on, then my output bits are coming on. So we can look at those bits, and I can tell you right now from that those two outputs are on. So that allows us to do something in the PLC world that we can do in the real world, but we have to have some extra hardware. We can turn on outputs based on whether other outputs are on. So like right here, we know this output's on and this output's on. We can monitor those as inputs. We can say, hey, go look at that input in the data table, and that input is output 4.1. And we can say, go look at the other input, and we can say, look at output 4.2. And if they're on, let's turn on a third output. Now, remember, we're not turning it on here. We're looking to see if it is on. Here, we're going to turn on another output, and we're going to make it 4.0. So again, this is an input that turns on that output. This is an input that turns on that output. Here, we're looking to see, is that output on? Is that output on? If it is, then turn on this output. So these do not change the state of an output. They look at the state of an output. Remember, their name is examine, see, look. This is the output energized. So this is just looking at these two outputs and saying, hey, if they're both on, let's turn on this output. So let's download that program. And we can see it's already on, but it takes both of those to be on to turn on this output. If we turn either of them off, that output's going to go off. And if we turn both off, obviously, both of them will go off. Well, what if we wanted it on when either one of those is on? Right now, they both have to be on this and this. Well, that would make an OR instruction. That would be a branch. And we'd have to drag this guy down into our branch, which is sometimes easier said than done. Let's do this. Didn't want to light up for me here, so we'll just do this. We'll cheat. Put 4.2 there, and then we'll get rid of this guy. Same essence. So before I had them side by side, and that was an and. This one and that one would have had to be on. Here, either has to be on, and we're going to be on. So I'm going to re-download this program, and I'm going to hit run. And notice when I turn on the first one, the third one's going to come on, or the third one, the first one's going to come on. You get the idea. And if I turn on the other one, it'll stay on. But if I turn them both off, or turn either one of them on, it's going to come on. So we get a lot of flexibility with the PLC because we can't readily do a lot of this in the real world without extra hardware. But here, it's just a matter of looking at zeros and ones in the data table. Now, we could do a lot just playing with this simulation. I could say, let's pretend bit 4 was a conveyor. Let's pretend bit 5 was a lamp. Let's pretend bit 6 was a pump. And we could watch it, but nice thing is this thing's got some built-in simulators. Here's a door simulator. And when we look at this door simulator, we see these push buttons, input 0, input 1, input 2. Notice they align with that I/O simulator. Inputs are 1, outputs are 2, inputs are 3, and outputs are 4. So we've got a door here. We've got lamps here, outputs. Remember, lights, we turn on and off, push buttons, we press, and they send us a signal. Here's some limit switches right here. Here's motor up, motor down. Those are outputs. We've also got a silo simulator with more inputs and outputs, lamps. And to get these I/O addresses here, we have to hover over them for just a second. We run out of room on the graphic, so you can just hover over and see the output addresses here. They're written. We can go to our traffic signal. There's a two-sided red light. There are some lamps. There are some push buttons. We can go to our batch simulator. And again, to get these buttons, we have to hover over them. And to get these, we hover over those. Those are lamps. So if we can't readily see an address, we can hover over it. I'll just do a quick example here. So I'm going to go to File, New, and I'm going to use the process emulator here. And I'm going to just make this mixer come on when I press and hold the start button. Now, that's a momentary start button, but I'm going to create a program that would do that. So I'm going to add an examine if closed. I'm going to add this start address to it. And if I close that button, push that button basically, I'm going to turn on the mixer. Now, this is not how this actually functions, but it will function this way, which is one of the cool things. So I'm going to download it, put it in run, and watch what happens when I hit start. Well, the graphic would normally show it. It's lighting up. Oh, I see why. No, it's not coming on. So let's try the heater. So normally you would see that mixer come on, but I'm using it kind of, normally we don't start the mixer by pressing this button. So maybe that's one of those little fallacies that it has. Like I say, it has very few, if any, but let's see if we can make the heater come on when we press the button. So let's try it. If not, we'll write something the way it's supposed to work. There we go. Heater's on. When I let go, heater's off. Heater's on. When I let go, the heater's off. So again, not how we would normally write, because what normally you would write with this is you would press start, either both or one of these pumps would come on. It's going to fill up. It's going to get to a certain level. We're going to mix it by then, turning on the mixer, may add some heat, and then we're going to drain it out and move forward. So I was kind of using this for something that wasn't intended, but you can see that this particular program does work here. Not sure why the mixer. Let's try it one more time to see if it's a fluke. I know the mixer normally works, but I think it's just because I was trying to do something outside the norm here. But let's see. I'll slow my simulation down just in case. Nope, won't turn the mixer on, but will turn the heater on. We can see it light up. I just can't see the spin here. Just to give you an idea, I'll write you a quick program. It won't take but a minute. So we'll write a program that basically turns on pump 2. Or excuse me, pump 1, and we want that pump to be on as long as the high level switch is not on, because if we keep pumping after the high level gets full, we're going to overflow our tank, which would not be cool. So let's see if that works. I like to write one line at a time when I'm writing code. So we're going to press and hold start. It should fill until we get to the very top, and then it should shut off. And it did, even though I was holding start. Notice it's no longer pumping. So now let's turn on the mixer, and what we'll say is if the fill light high level is on, let's start the mixer. Now, normally we'd have a timer, but I just want you to see the mixer does work since it decided not to. So I'm going to go up here in the simulation, reset simulations, and I'm going to re-download this program and hit run. And when I press start, it'll start filling up. It'll fill till we get to the high level sensor and then cut off, and then the mixer will come on. And there it is. You can actually see the mixer running now. So there's a lot of versatility with this trainer, or with the simulator, and obviously there's meant to be more to this simulator. I just wanted you to see that. So the nice thing about this is whatever you're doing here as far as programming and understanding translates readily into the real world. So this is the simulator at its finest. This is why, even though the graphics are from 1995 or somewhere in that era seemingly, I like this program because this is the disc that you can carry with you. You can practice these skills, you can hone these skills, and you can keep these skills. And it's fun to play with, in my opinion. Maybe I'm easily entertained, but I think as you play with it and get better at programming, you'll enjoy it too. So there it is. And as always, if you have questions, let us know.